y'all's vocabulary words and use y'all's books, because I'm going to ask you questions for what words mean. And so all you have to do is just pretty much read them off in your book to me. So, this is an overview just for Chapter 10. Miss Cameron is going to go a little bit more in depth into Chapter 10 next week. You have it today, Monday, and Tuesday. So it's really beneficial to you to really pay attention all 3 days, because with how y'all's tests are set up this time, you have to go through Chapter 10 really fast. So, and we're going to start. So Chapter 10 is about temperature and heat. That's the main bulk of the chapter. All right, temperature. Y'all just got done studying kinetic energy. What is kinetic energy? That's right, the energy of motion. What you're going to learn is that temperature has everything to do with kinetic energy. Temperature is the measure of the average kinetic energy of the particles in an object. So your temperature is based off of your kinetic energy. The more kinetic energy there is, the higher the temperature will be. So certain things like an ice cube doesn't have a lot of kinetic energy. Whereas a stove, when you're cooking something, has a lot. And y'all know this just from personal experience, but it's kinetic energy that affects that temperature. All right, measuring temperature. What is this? Okay, that's right. And that's exactly how you measure the temperature. Now, what it uses is something called thermal expansion. Now what is thermal expansion? I know it's one of your vocabulary terms. That's right. It's an increase in the size of a substance when it's heated. So when something is heated, it expands. Now, how thermometers work is they have either mercury or alcohol. And both of those substances expand a lot when they're heated. And so that allows for, when it's colder, it to be down here. But then when it warms up, it increases from that small amount all the way up to where it is. So that's how it works, is by thermal expansion. Now, one temperature that y'all have to know about is absolute zero. And absolute zero is a temperature at which all molecular motion stops. So this has never been reached in a laboratory, because there would be pretty much no life going on. The only close that scientists have ever gotten to is in a lab setting. All right, temperature scales. When you're watching for how hot it's going to be tomorrow, or how hot it is today on the new weather, what scales do they use? Like they say 100 degrees Fahrenheit. That's the main one that everybody knows about. We use that more in America than anything. Now, there's another one. Does anybody know the other one? That's right, Celsius. Those are the main two y'all have to be concerned with in this class. Is Fahrenheit and Celsius. And there are two equations for going from Fahrenheit to Celsius, or from Celsius to Fahrenheit. And both of those equations are right here. Now, going from Celsius to Fahrenheit. So if you have something that's 25 degrees Celsius, what you do is you just put 25 degrees right here. And then you times it by 9/5 and add 32. Okay? And then Celsius is very similar but a little bit different. If you have something in Fahrenheit, you will take that number and subtract it by 32 and then times it by 5 times. So Fahrenheit is almost always going to be, when it's a warm temperature, it's going to be a higher number. For instance, like the boiling point of water, it's 212 degrees Fahrenheit. But the boiling point of water in Celsius is 100 degrees Celsius. And there is one other type of scale that many scientists use, and if you go to a university in the future, go to college, you will use this. And it's called Kelvin. You need to know this a little bit, but y'all aren't going to be working with it too much in this class. And the way you convert to Kelvin is by whatever it is in degrees Celsius, you add 273. And that's it. And just to give you an example of how different these scales are, is this. Remember I just talked about absolute zero? This is the differences in numbers. It's negative 459 degrees Fahrenheit, negative 273 degrees Celsius, and 0 Kelvin. So you see a wide range, a great difference between those scales. All right? Now, let's go. Okay, now this is just a little sample problem to give y'all, to let y'all look at for things y'all will be doing later, possibly on the test. Your body temperature is normally 98.6 degrees Fahrenheit. Now, how do we convert that to Celsius and to Kelvin? Which one of those equations are we going to use first to go to Celsius? All right, here we go. And this is the equation. Okay? So, you're just going to plug 98.6 into where it says degrees Fahrenheit. And it ends up being 37 degrees Celsius. Okay. Next, you want to get Kelvin. Okay? So, here's the equation. So, if it was 37 degrees Celsius, what is it going to be, Kelvin? Y'all have a calculator.
37 degrees Celsius.
That's right. That's right. 310. That's right. Now, heat. And this is section 10.2 in your book. Okay. Heat is the energy transferred between objects that are at different temperatures. Now, what type of energy is heat? That's right. Thermal energy. That's the type of energy that's used. Okay? And thermal energy is the total kinetic energy of the particles that make up the substance. So you see how heat and temperature and kinetic energy all relate. Now, there are three types of transfer of thermal energy. And one is conduction. Now, who knows what conduction is? And that's right. That's right. A good conductor is a metal. It's by direct contact, and I'll give you that. Thermal conduction is the transfer of energy from one substance to another through direct contact. So you have to touch something. So if you touch an ice cube, or if you touch a stove, that's conduction. Thermal energy is being transferred. Okay. So, and you led into that, the two types of things going to conduction. One is called thermal conductors, substances that conduct thermal energy very well. And then one is thermal insulators, a substance that does not conduct energy very well. And a thermal conductor, a good example is metal, like you had already said before. And then a good example of a thermal insulator is blankets or coats. For instance, whenever it's cold and you put a lot more clothes on, you put a thick coat on, this is what's taking place. This is why it keeps you warm. Because that body heat that you're releasing to the energy, that coat holds that heat in. And so therefore you don't lose all your body heat. And it stays in the coat, and it keeps you much warmer. So that's how anything that keeps you warmer, that's how those work.
DJ.
Alright. Second type is convection. It's a little bit different than conduction, but convection is a transfer of thermal energy by the movement of a liquid or a gas. So this isn't direct contact. A good example is a fire. You know, you don't put your hands right in a fire. I mean, some of you may, but that probably would be too smart. But you get the gas that's rising from the fire that's very warm. And so that's the way that that's warm. I've got an example of right here of a pot on a stove with boiling water. And can y'all think of both types, conduction and convection, are both taking place when you boil a pot of water on the stove? I want to see do y'all know how that takes place? Do y'all know how the two take place?
Conduction is like fire touching the pan, right?
That's right. That's right.
Like the convection is the boiling water turned to steam.
That's right. That's exactly right. You have the stove touching the pan, and so that's conduction. And then you have the boiling water, which produces a gas that's warm, and it leaves. But that's how convection takes place. So that's exactly right. And the very last type is radiation. And many of you know this, but it's thermal energy transferred through electromagnetic waves. The best example of this is the sun. This is UV waves, infrared waves, and microwaves. And if you tan or anything like that, that's how radiation is passed to you. That's what gives you a good tan, is the radiation and that thermal energy that's coming to you. Okay, specific heat. Specific heat is the amount of energy needed to change the temperature of 1 kilogram of a substance by 1 degree Celsius. So how much energy needs to be put in to that substance? How much do we need to add to raise the temperature by 1 degree Celsius? And the higher the specific heat of something, the more energy it takes to increase its temperature. And a good everyday example of this is when you go to a pool in the summer and it's really hot outside. You know, it's like 100 degrees. But then you get into the pool and what does it feel like? It's cold. And that's because water has a very high specific heat. And it takes a lot longer to put enough energy into that water to warm it up than it does for the air or for the ground surrounding that pool to warm up. So therefore, you feel a lot hotter when you're outside of the pool and then you get in and it feels kind of cold because that water is much lower in temperature. And that's why, because of the specific heat. Alright, now one example of just the type of problem that you're going to see in this chapter is calculating heat. And it is specific heat times the mass times the change in temperature. Okay, and your change in temperature is your final temperature that you want minus your initial. So, look at this problem and see if y'all can just tell me what numbers go where. Right, okay. What numbers in these three parts of it, the specific heat, the mass, and the change in temperature, what numbers in this problem go into that equation? How will we set that equation up using this problem? And this is in your book if y'all want to do that. Alright. Okay. That's part of it. Now, your change in temperature, I'm going to go into that. Your change in temperature is going to be 80, which is going to be your final temperature. And so you're going to put that in first. And then 25 is your initial. So your change in temperature is going to be 80 minus 25. And then your mass is you have 0.2 kilograms of water. And so that's going to be your mass. And then your specific heat is 4,184 joules per kilogram times degrees Celsius. So that's a very high specific heat. That's why you see water takes a long time to warm up. So, and all that, you put those in and times it, and that ends up being like 46,000 joules. So it takes a lot of energy to just raise the temperature of just 2 kilograms of water by 55 degrees Celsius. All right. I know y'all had chemistry already, so y'all should know a lot of this. The 3 states of matter: solid, liquid, and gas. And then a change of state is changing one substance from one state of matter to another. So going from a solid to a liquid, or a liquid to a gas. Now, one thing that's you're going to see in this chapter is how when you're adding energy to something that's, say, negative 10 degrees and it's an ice cube. We're going to use water. And you want to make it steam. You want to make it a gas. This is how when you add energy, you've got temperature. Sorry if I can't see this. And you've got energy right here. So let's say you start off right here with a negative 10 degree block of ice cube. All the energy, what's the melting point of water in Celsius? Do y'all know? That's the boiling point. It's 0 degrees Celsius. So you got a negative 10 degrees block of ice. You have to raise that all the way up to 0 degrees Celsius. And so all the energy you're adding is going to be spent in raising that temperature. Okay? Then you can't raise the temperature anymore until that entire substance has been changed from a solid to a liquid. So if you're adding energy, it's going to look like this. The temperature is not going to raise while you're converting that solid to a liquid. But all the energy is just going to be for making that conversion, making that change of state. Now, once you get it all converted to a liquid, you're going to raise that temperature again to make it become a steam or make it gas. So all the energy is used to raise, and you said a second ago it's 100 degrees Celsius. All the energy added is going to be used to raise the temperature to 100 degrees Celsius. And then when it gets to 100 degrees Celsius, the temperature won't raise anymore until all that liquid has been converted to a gas. So that's just your basic setup of how a change of state graph is used. I know that can be a little bit confusing, so hopefully I helped you out. Miss Cameron will go a little bit more in detail in that next week. All right, and chemical. And y'all seen this. The chemical change is when a substance changes into a whole new substance. So you change its chemical properties. And there is tons of chemical energy in your food that you eat. And the unit that you use to measure this is a calorie. And I know many of y'all have heard of calories. And that's just the unit used to measure chemical energy in food. Okay? And then just your last section includes some basic ways that we use this in today. These are heating systems that are used in your home and insulation. And these are cooling systems, which is air conditioning. Then a heat engine, which is just your core engine, is used that way. And then thermal pollution. And that's how heat is really used today in society. So that is it.